signed up to please sign up. And second, those of you who are here will therefore hear the second announcement. So only those who are on this sheet and are not here today need an email from me to send to tell them that we are moving Monday lectures. I would therefore ask you, even those who have signed up, to next to your name put a check mark or an X to indicate that you were here today. I'm not actually checking if people are here, I don't care. But just for today, because those of you who are here, I will not need to send an email to everybody else who is on this sheet but hasn't checked the name. I will then send an email. Make sense? Okay, good. So please check next to your name or sign up if you haven't, and then put the check next to your name, obviously. Homework number 1 will be posted Monday, this coming Monday. It will be due a week later. It will cover everything we've said last lecture, everything we'll say this lecture, maybe a little bit from Monday's lecture. That's why we are posting it on Monday. And as you can see here, Monday lectures have been moved to TBM at the other side of campus, lecture room B. I have no clue where it is. And the irony is that by asking to move, and they moving us over there, essentially we will reduce the number of people showing up on Mondays, because nobody in their right mind will go from here to TBM just for this lecture, or not nobody, but quite a few wouldn't. As a result, I would expect the number of people will be lower anyway, but still, just to play it safe, because we had the trouble last Monday, the room didn't fit everybody. We now have a bigger room at the other side of campus. Any questions on any of this, please?
Is there also a time for the deadline?
Yeah, that will be posted. Usually it's 5 p.m. of that day, and it's not 5:01. Those of you who know me from other courses, it's 5 p.m. Okay, so we are continuing our discussion on classical laminated plate theory. And last time we essentially finished by simplifying a lot of things. And instead of using stresses, we use integrals of the stresses, or integrals of the stresses times the z through the thickness coordinate, which gives us moments. So we have the so-called stress resultants, which are the 3 forces per unit width, x, y, and xy being the shear force, and then the 3 moments per unit width. The sign convention is as shown here, and that's the one everybody should please try to be using. With this in mind, to just show a direct and obvious, but still to reinforce an obvious relationship, if I have a certain force, this is units of force now applied, if I divide that force by the cross-sectional area, width times h, the height, I get obviously the average applied stress. And this average applied stress is then, by definition, the 1 over the thickness times the integral of the actual point-wise stress. And because this, we just said, here is the nx force per unit width, we can then arrive at this relationship, which, even though obvious, many people tend to forget, and it can be quite useful many times. So we then said, okay, we have this equation 1,1 that we introduced, and I will show that again in just a second. And we also introduced the mid-plane strains, 2 normal strains and 1 shear strain, mid-plane of the laminate that we are dealing with. And we said if we take this equation 1,1, so let me fly back, which is here, this equation 1,1 relates stresses in the coordinate system 1, 2, which is not necessarily aligned with the fibers in any ply, to strains in the same coordinate system through these coefficients that we defined and even calculated a little bit last time. So if I take, let's say, the first one, and I integrate through the thickness, I will arrive at the relationship shown here at the bottom where the nx, because that's the integral of the stress through the thickness, relates to the three strains via three elastic properties, which are three entries in the so-called A matrix, and they are membrane properties because they refer to only in-plane performance of the structure. If I have an applied force, I get, in general, three strains in my laminate. If I have an applied strain or three strains applied, I end up with in-plane forces. One important characteristic for a composite, notice the presence of this term. Basically, I can apply a axial force and get a shear strain, or I can apply a shear strain and get an axial force. Not for every laminate, but in general for laminates for which this term A16 or this integral here is non-zero, that would be true. In metals, you cannot have that. You cannot have a uniaxial load and cause shear strain. So if I did it for the other two equations relating stresses and strains, I would get two more equations that in matrix form gives us the so-called membrane behavior, where the in-plane forces are related to the in-plane strains. And the A's are given as integrals of these QIJs, the QIJs being the stiffnesses. And because through the thickness each of the QIJ is constant, I can replace the integration with summation throughout all plies, as long as I calculate correctly the integral dz, which is just the z coordinate at the top of the ply in question, which is the kth ply, minus the z coordinate at the bottom of that ply. What that means, to repeat and reinforce a little bit, is that if I have a laminate if I define z equals 0 here, let's say, that becomes now my z0, and as I integrate through the thickness, I can determine the course for each ply. I will have a zk at the top and a zk minus 1 at the bottom of each ply, which are the coordinates with respect to my origin. And that gives me every single term in the A matrix. That's the end of last lecture. Just to recap and also to create an analogy with what we're about to say now, which is the bending behavior or out-of-plane behavior. Now, in general, for any structure that we will be dealing with, it suffices to assume that the strains through the thickness are linear. Basically, they consist of a constant term which represents the strain in the midplane and a linear distribution of strain, linear being in z, z being the out-of-plane coordinate, and the constant of multiplication here, or constant of proportionality, happens to be the 1 over the radius of curvature. That's just standard mechanics for basic plane stress type of deformation out of plane. So the strain now at any location through the thickness is therefore a linear function, and if I replace my second derivatives shown here with a common symbol kappa x, kappa y, kappa xy, which are the three curvatures, I can write in a more concise way the same thing. So this is the general case where I can have both stretching and bending, and just to simplify things, let's say I only have pure bending. Pure bending means that there's no stretching. Remember our Bernoulli-Euler beam types of assumptions. If I have no stretching of the midplane, then the three midplane strains are 0. And by integrating now, again, those 1-1 equations, so I'm flying back, see how fast I can find it. So these equations are still valid, but now we will replace the strain with its linear dependence, and we will integrate this relationship through the thickness, provided we multiply by z also. It appears arbitrarily we multiply with things, but the only reason we do this is because we want to refer everything to the force resultants nx, ny, nxy, and the moment resultants. And we know that the moment resultants are integrals of stresses times the out-of-plane coordinate. So I basically take that first relationship of those equations and I multiply by z and integrate, and we would get this plus additional terms. I forgot to say plus here, additional terms. But this is the strain now, epsilon, oops, where am I? Z times this second derivative with a minus sign is the epsilon x strain, which is shown right there. So this is the mx by definition, and in the general case when we have the epsilon x, the epsilon y, and the gamma, the kappa x, kappa y, and the kappa xy, we will generate the general relationship which involves q11, q12, q16. The 2 here comes from the fact that our curvature relationship here for this twisting strains involves this factor of 2. So I can then, for pure bending, say that the curvature, the radius of curvature, which is essentially this second derivative, is 1 over the radius of curvature in the x, and then 1 over the radius of curvature in the y direction, and then the this one is a weird combined radius of curvature that I have no feel physically what it is, but it's there. The bottom line is those will be constant for pure bending, because we're saying that basically the radius of curvature is locally constant. That means I can take them out of the integrals. So this second derivative here becomes a kappa x with a minus sign, it's lumped in here, kappa y here and kappa xy, and I'm left with these integrals, which again, same way we did for the in-plane behavior, can be integrated throughout the thickness, and because throughout the thickness each of the q's, which are stiffnesses, are constant, we can make them into summations, and the z dependence becomes this integration of z squared, shown here at the top right, which becomes z cubed at the top surface minus z cubed at the bottom surface. So we can then call these conveniently d11, d12, d16, and therefore in general, if we only have pure bending, the moments per unit width are related to those curvatures, or kappa x, kappa y, and kappa xy through this matrix. And you might wonder why all of a sudden we started with A and we jumped to D. There's a B, but there's no C, for reasons that I hopefully will remember to tell you in just a second. As if this were not enough, composites have coupling or exhibit coupling performance in general. Basically, you can have in-plane load, and as we said, you can have shearing as a result of it, which is a mild case of coupling, stretching, shearing, coupling. What makes things worse is you can have an in-plane load and generate an out-of-plane bending, or can have a pure bending moment applied and generate in-plane loads. And the way to see that is, again, if we go back to this same equation that relates stresses to strains, but now include the in-plane and the out-of-plane dependence, and we integrate with respect to z directly instead of multiplying by z and integrating. So we take the basic relationship, integrate with respect to z, which means this integral of sigma x will become our nx, the force in the x direction of the laminate. And then the q11 integration will become the a11 we saw just a little while ago, the a12 and the a16, which are lumped here. And then the remaining are new quantities, which are now the q's times the integral of z dz instead of q times the integral of z squared dz or q dz. So this new integral is now our B matrix, so that's where the B comes from. And we have, as a result, the coupling matrix that tells us by how much the structure would bend if we were applying an in-plane load, assuming it's a composite structure. And therefore, we have the overall relationships. If we put them together in matrix form, we have the forces, nx, ny, nxy, and the moments, which basically are related to the mid-plane strains and the corresponding curvatures. Now, for a given loading situation, the mid-plane strains and curvatures are supposed to be constant. So once you know the loading, you can find the curvatures, or once you know the curvatures and the mid-plane strains, you can find the loading. Notice, of course, this is a pretty ugly-looking matrix. There is the A part, which relates directly in-plane properties in terms of loads to in-plane strains. There's the D part here, which relates just the bending with the curvatures, and then the B matrix will couple in-plane loads with out-of-plane curvatures or in-plane strains with out-of-plane bending loads. So in general, this is all there, which is quite unfortunate because it complicates things. So this is the A, the D, and the B, and there is no C because C in general is either the compliance matrix or a stiffness matrix, depending on how you formulate things, and people had been using C for a very long time before the composite theory had been formulated, and they decided they did not want to create a confusion, so they jumped from B to D instead of from B to C. That's the main reason. Two important characteristics of certain types or certain classes of laminates. If I have a symmetric laminate, then the B matrix is 0. Symmetric means that with respect to my mid-plane, which in this case with my 4 laminates is just 2 layers above and 2 layers below, with respect to this mid-plane, a certain ply, which has an orientation theta, let's say, will have a corresponding one at exactly the same mirror image location, which has exactly the same orientation. So with respect to the mid-plane, this would be a symmetric laminate because the theta 1 at the top ply is the same as the bottom one, and the theta 2 at the mid-plane or the ply next to mid-plane is equal to the one right below the mid-plane. Once you have this, you can basically show that if you go to our B matrix definition, so I'm jumping back for a second here, you can show that these terms will cancel out because whatever you get above the mid-plane as a contribution will be cancelled by whatever you get from below the mid-plane. As a result, the B matrix is 0, which simplifies things. That's one case. The other case is the terms that relate in-plane load with a shear strain or in-plane shear with an axial strain there. Those A16 and A26 are 0 if for each plus theta, which can be anywhere in the Steitting sequence, there is a minus theta anywhere in the Steitting sequence. They don't have to be next to each other. They don't have to be in the symmetric locations. As long as for every plus theta you have a minus, then you are fine. And as a result, A16, A26 is 0, which means you cannot couple the in-plane stretching behavior with the shearing behavior. Now, as a nice add-on is the question, okay, if you look at my D matrix, the D16 and D26 terms, what they do is they couple torsion or twisting with bending. So if I have pure bending, actually the structure will also twist, or the other way around, if I have pure twisting, the structure also bends. So for this not to happen, so this type of coupling not to be present, we need D16 and D26 equals 0. So can anybody tell me, either from previous knowledge or very quick thinking, what types of laminates have D16 equals D26 equals 0? Gentleman there? Okay, I'll give you that. Good. Any other case? Okay, that's also true. Excellent. Now, suppose you have some plus thetas and minus thetas. Can you create a laminate? Everything you said is perfectly correct. There's one more general case.
That they are like non-symmetric to the midplane. So on top you have plus theta and below minus theta.
Excellent. Yes. So anti-symmetric. So if at a certain location I have a plus theta and the corresponding location with respect to the midplane I have a minus theta, and that is valid for all the plus thetas and with the minus thetas, then all the D16 and D26 terms will cancel out because the contribution above and below the midplane cancel. That's very good. Now, in general, we are not given the strains, but we are given applied loads. So if you looked at the relationship we had before, it was relating forces to strains and curvatures, and that's not the most convenient way. This is much more convenient because typically we're given forces and moments, and we need to calculate strains and curvatures just because that's very useful for calculating failure eventually. So all you do is you go back to your linear algebra and you take this huge matrix and you invert it. Or you ask MATLAB to do it, and I invite you to try to do that with a good size laminate, not 090, but something complicated. In most cases, it can't invert it. Not that it's not doable, it's just that numerically it becomes quite difficult. I've had a student doing that in general, and it just was a nightmare. And of course, you cannot have symbolic manipulation to do it. Maple, it's a 6x6 matrix. You get 60 pages for each term if you get that. It turns